Sure, so we'll be doing geometry now. Everyone's favorite subject. So, what I expect you guys to know is basic properties of lines, angles, parallel lines, perpendicular lines, and considering that you're here, I'm sure you guys are comfortable with that, and yeah, so I don't think there's any need for me to go over school geometry, if I may say. But however, I will start with probably the most basic but like very important structure, which are triangles. So yeah, triangles are quite important because in almost every geometry question you do, there's always a triangle of some sort, and it's useful to know all its properties and know how to apply them well. So we'll start off with what it means for triangles to be congruent and what it means for triangles to be similar. So, does anyone know what it means for triangles to be congruent? Yes, over there. Yes, precisely. So the word congruent, you'll see it as well in number theory when you do modular arithmetic, but what it means is exactly the same or equal. So if two triangles are congruent, one may expect that they're exactly the same. So if we have roughly this triangle and maybe that, they look the same, they're identical to each other, so they're congruent. And say we have another one where it looks like this, then that's probably not congruent to that. But I mean, there's a better definition for it. It's triangles are congruent if all their sides are equal. So if this side is equal to that, that's equal to that, and this side is equal to that side, then it's easy to see that they're the exact same triangle. So yeah, and the symbol we use is these three lines. So if you wanted to say, call this A, B, C, this triangle A, B, C, and this E, D, E, F. So we would say triangle ABC is congruent to triangle DEF. Cool. So that's the symbol we use for exactly the same. And similar triangles are defined in it's similar. So similar triangles are when all the angles are equal, but they may be different in size. So if we had another triangle here, which was slightly smaller, but looked so similar, meaning they look the same, but just like this one is scaled down a bit. So they have the same angles, but this one is just smaller. So if we had this, call this GHI, so then this triangle, which is congruent to this one, would be similar to this one, because this angle corresponds to this angle, this corresponds to this, and this angle corresponds to this. And the notation for this, in school they prefer to use these three lines in three, yeah. And well, I prefer to use this. It's much easier to do instead of the whole three-line thing. So you would say triangle, and also to note that the order of congruency is important as well. So AB matches to DE because they're the same length. So AB and DE follow that order first, and BC is equal to EF. So BC and EF have to be in that order as well, in second and third, and similarly AC and DF are also equal. So you can't write, because I once made this mistake and I thought it was right and ended up getting a mark off. I wrote ABC is congruent to triangle, say, DFE. So that's not necessarily true because the order of the triangles actually matters. So you can't this triangle in essence is not the same as this because of the order. But yeah, so just be careful with that, because a lot of people make that mistake when they don't consider the order of the similar. Same thing with similarity. When you write two triangles similar, you actually have to consider the order. So you write triangle ABC here is similar to triangle GHI in that order. Or if you like another order, maybe triangle BAC is similar to triangle HGI. So yeah, the order is important. Yeah, so that's pretty much covered. And oh yeah, for similar triangles, the ratio of the sides is consistent, meaning if you take the first two sides, the two sides which are correspond in a way to each other, so here we know that AP corresponds to GH, we know that AP over GH, and these two correspond to each other, AC and GI is equal to AC divided by GI, and finally the last pair, which is BC over HI. So yeah, this is very important, especially when you have a question with a lot of angles. You know, angles are equal and stuff, but you want to know something about the sides and the ratios. So it just converts whatever you know about angles to what you know about sides, because that's a lot of geometry problems where you like just know all the angles, but if you don't know any of this, you can't convert it to what you know about the sides. So yeah, this is probably the most important thing about similar triangles. Yeah. And maybe just to notice that congruent triangles are also similar, but this ratio is 1 because it's the same. Because if they were congruent, then AB is equal to GH, so everything is just the same. So that's just sure. Okay. Next, I'll move on to the midpoint and proportionality theorem. Whenever you write geometry proofs, you shouldn't assume stuff. Maybe I should have said this in the beginning. Because sometimes you... Okay, sure. Yeah. Okay, you shouldn't assume stuff, because I was marking your scripts today and some of you assumed like things that were not necessarily true. So that's just like it literally... Because everything that follows there is based on an assumption which is probably not true, and then everything is just false. So you should be careful on what you say is true, and if you see a sketch and you think this might be true, then try to prove it so that you're sure, because the sketch could be drawn not to scale or something. So this probably applies to all the subjects, but in geometry especially, you should prove everything. If you, because I know a lot of things look like they're something but they're not, so just try to prove it, or yeah. So midpoint theorem. So the midpoint theorem states that if you have a triangle and you take the midpoint of two sides, so that's equal to that midpoint, meaning the point away, that's equal to that, and that's equal to that, and you connect these 2 points, then the midpoint theorem states that this is parallel to that, right? So yeah, as much as we'd like to be like, okay, midpoint theorem, yes, that's true, and we also have to prove that. We can't just accept things blindly. We have to know why is this actually true. And I'll demonstrate something that you often use in geometry, which is a construction. I mean, I think there's several solutions to this, but I'll show you the one that I came up with just. So, yeah.
I think it is parallel
these two triangles, okay, let's label them A, B, C, maybe this D and E. Which two triangles have the same altitude?
I'm saying the height from B to A, the perpendicular height, and from C to A is the same.
From B to A. The height, but you can't have a height from a point to a point. It has to be from a point to a line. So yeah. So yes, so there's several ways to do this. So we'll use construction to prove that that's equal to that, using what you've already learned about similar and congruent triangles. So any suggestions? So many hands up. Yeah, quick hand came up first.
Could you not draw a congruent triangle to ADE and
Two?
and then, sorry, it sounds like, and then add it onto the line EC so you create like a parallelogram?
Okay, I get what you mean. That's the one that I'm going to come up with. Okay, sure. Any more ideas?
Can't you prove that they're similar, and then with that you can find all the angles, and using the angles you can say that the corresponding angles are equal. I mean, you can find that two of the angles are equal, therefore they're corresponding, and therefore the lines are parallel.
Okay, sure. Okay, it looks like all of you have the right idea, but yeah.
But they all similar because angle A is common, and then D, and then AD, and AB, and AE and AC are in ratio.
Oh, okay. So yeah, I get what you mean, but we still haven't used that definition of if two sides are proportional and the angle between them is the same, then they're similar. So we still don't know that yet. So, but I understand what you mean. So what we do is we construct a point such that. So yeah. Construct a point X here. Oh yeah, sorry, I forgot to say, the midpoint theorem also says that BC is twice DE. So maybe BC is 2 times DE, and okay, so yeah, we construct a point such that a point X on we extend DE and construct a point X on DE such that DE is equal to EX here, right? So a lot of you can see where this is going. So we know that this angle AED is equal to angle XEC. So these two angles are equal because they're vertically opposite, as you'd say. So now what can you see about these two triangles? Yeah, they're congruent, right? Because this side, and this side, well, this side is the same as this side, and the angle between them is, yeah. So we should have triangle AED is congruent to triangle CEX, right? Now, since they're congruent, you can say that side CX is equal to AD because all the sides are equal to each other.
Wouldn't you use the congruent sign, not the similar sign?
Oh, sorry about that. Okay, yeah. So that's equal to that, and also it gives us more information about the angles because we know that congruent triangles also have the same angles. So that we already do the 2 lines is equal to that, and is equal to that, right? And then what can we see about the lines CX and AB? Since this angle is equal to this angle, since this angle is equal to this angle, what can we say about the lines AB and CX? Yeah. because they alternate interior angles and they're equal, so these two lines must be parallel. Cool. So those are parallel. And we also know that this line is equal to this line, right? So therefore this must be a parallelogram, right? And so this also then if this is x, and since by construction this was the same length x, so the opposite sides are equal, so this has to be 2x, right? So we have shown that these two lines are parallel since this is a parallelogram. So we've shown this first part to this, and we know that since this is x, this has to be x, and this is 2x, so we've also shown this part. So the midpoint theorem holds. Yeah.
Using the two angles that you did to prove that there were alternate angles, aren't you proving that AB is parallel to CX?
AB. Yeah, that's what we did.
Were we not trying to prove why DE is parallel?
Oh,
to
okay. So
BC?
so maybe you missed the date, but BD is parallel to CX, right? Because BD is the same line as AB, right? So you agree that these two are parallel, and these two are also equal because this was equal to this by congruence, and this is equal to this because by the so opposite sides are equal and parallel, so it has to be a parallelogram by properties of a parallelogram. So therefore that's also parallel to that. So opposite sides are equal and parallel. Anyone with any questions so far before I move on? Maybe a more general case of the midpoint theorem would be the proportionality theorem. So this talks about if you have a triangle and you have a line that's parallel to one of the sides, and it says that the ratio of this to this is the same as the ratio of that to that. So keep that in mind. That's also pretty useful, and it has a very similar proof to that, or maybe okay, maybe let's try a different proof to this. Let's call this ABC. And this point D, and this point D. Right? So we have, since these two are parallel, we have that that's equal to that, and that's equal to that. That's equal to that, that's equal to that. And this angle is just itself. So ADE and ABC have the same angles, because that's common in both of them. Angle D and B are equal, and angle E and C are equal. So triangle ABC is similar to triangle ADE. Yeah.
So basically, it doesn't have to prove it because on similar, the sides have to have the same ratios.
Yeah, but and then with a bit more algebra, okay, you have to show that, because what this gives is that AT over AB is equal to AE divided by AC. So you have this over the whole length is equal to this over this whole length. But what we try to say is just this over only this is equal to this over only this. And that takes a bit more algebra. So call this A, C, and D. So by this AD is just A, and then this over A plus C is equal to B over B plus D. Is everyone with me here? Because we're just turning these sides into what I've labeled. So A plus, so all of this. And then now what we're trying to do is get rid of the A plus C into just A and C. So what I do here, it looks like if I just take the inverse of both sides, I can get rid of A over A, because then it's just 1. So I just say, which implies that A plus C over A is equal to B plus D over B. I'm sure everyone can see what I did here. I just swapped them around, because if they're equal, then the inverses are also equal. So A over A is just 1 plus C over A is equal to 1, because B over B is 1 plus D over B, and then this one, just get rid of it. So C over A is equal to D over B. And then just taking the inverse just shows that A over C is B over D. So yeah, also quite useful to use. But this is if and only if these lines are parallel. If they're not, as I said, don't assume they're parallel. Don't be like, oh yeah, I've seen something similar before. But only if they're parallel. So never assume that they're parallel. You'll probably get no marks for it, like at all. So try to prove that it's parallel first, or or if you can't, then it's probably not, and you probably shouldn't try to use something that you've assumed. Any questions? Oh yeah, and your test this morning, question 2 was mostly this, but with a bit of areas, so it was just chasing ratios using areas. So yeah, ratios are quite useful. If geometry is not all about angle chasing and finding angles and filling everything in, it's also about turning something that you know about areas or angles into what you know about the sides and about the areas. So yeah. Some circle geometry. Who's actually ever done a bit of circle geometry before? Okay, that's like half of it. So maybe you guys might find this very basic, but I really do have to go through everything. And yeah, you guys can work on this. Right? So does anyone, okay, since you guys have done geometry, what's the definition of a circle? Yeah?
I don't know, but like something with an infinite amount of sides.
Okay, close. Okay, like I'm hearing infinite amount of points, infinite amount of sides. Can anyone put it together and give me a proper definition for it? Yeah?
I'm just gonna guess here.
Okay, sure.
Something that has a point that is the same distance from everything else in the shape.
Okay, sure. Yeah, that's good enough. I mean, all of it combined, all of your definitions combined, that's good enough. So the formal definition for it would be a set of points which are equidistant from another point called its center. So equidistant meaning distant from a certain point, meaning they are all the same distance from a certain point. So if you think of it, that's exactly what a circle is. You have its center, and then you have all these points which are radius r from it. And someone said that it's infinite of them, which is correct. So it's just a set of points that are here, and they form this thing called a circle. So that's what the definition of a circle is. Cool. And some terminology to go over, because yeah. So you have a circle, and this thing around is called its circumference, right? So all these points combined as a figure, it's circumference. And if you take a piece of this circumference, so maybe from here to here, and you consider that only, you would call that, yeah? No, it's not
An arc.
an arc, yeah, exactly. So if you take a piece, so let me just read here, a piece of the circle, call this an arc. An arc, right? So, and if you were to take 2 points on the circle, let's use these same 2 points, and connect a line between them. It's called a chord, yeah. So that's the chord. So this line here, the chord. And maybe a special chord, if I may say, is the diameter, because it passes through the center. So we have a chord that passes through the center, it's the diameter. It's still a chord, even if it's, yeah. And yeah, is that all? And oh yeah, a sector is, if you consider, it's like a piece of the circle. So if you take something from the center, like a slice of pizza, kind of. So this is a sector. So this whole thing would be a sector of the circle.
Also in between two radiuses.
Yeah, yeah, sure. And yeah. So if you have a circle and you have some chord, some points A and B which you join to form a chord, then the first theorem which you'll be doing, and probably without proof, is the fact that if you subtend an angle, meaning if you fix these two, pick another point and draw the angle between these two, and or you pick another point here, let's call this C1 and C2. So this is what when I say subtend, I mean fix these 2 points, choose another point, and consider the angle between AC and AB and CB. So that and that. So the first thing that almost everything you're building upon is the fact that that's equal to that, right? Regardless of where it's chosen, regardless that it's on the same side of it's on the same side of the circle. So maybe not here, can't be here, has to be on the same upper side. So there's also a property of when it's on this side, but I'll go over that later. So that's, so any point here is equal. Here as well, even no matter else, there's all these angles are equal, right? Because the reason you write for this is because these are angles which are subtended from the same chord, so they're all equal. So it's very simple. And something that comes from this kind of is the fact that if you have 2 chords, say AB and CD, right? And these 2 chords have equal length, then they subtend the same angle. So how would you try to prove this? So since you already have that, okay, all of them are equal if they subtended from this chord, but then you're saying now it's not only for one chord. You're saying if these 2 chords are actually equal in length, then they actually subtend the same angle, meaning that this would be equal to that, even though this is not the same arc, but they have the same length. So it's not really a hard proof to think of. It's just a way of thinking of it. So any suggestions? Suggestions? Okay, so how you think of this is that if you rotate the circle, right, you're not changing anything in essence. So this, if you consider this chord, it's just this chord but rotated because they're the same length. So if you had to move this point, this to here, rotate it in some way, then this point will also move to here because it's literally just rotating the circle and they have the same length, so they fit perfectly together. And so then it's essentially the same chord but at a different rotated level, so they're equal. So it's not really easy to see, but it's not a hard proof to think of. Yeah.
So I didn't really get you. Could you please go one more time? Why C1 is equal to C2?
C1, and so we take this as a property of circles. We don't actually prove it, but we do it because A and B are fixed. So we choose any other point on the circle. So that's why I'm calling them C1, C2. Well, except on this side, on the upper side of the circle. And then all these angles are equal because they like the angle between B, C, and A, but C varies upon the circle. So, yeah.
But if you don't include the ones on top and you only choose points at the bottom, will those also all be equal?
Yeah, precisely. So if you have, because remember it's symmetrical, I didn't assume anything about the top or bottom, so I could have just started from the bottom. I could have said here and here, right? So let's call these D. So this is D1 and this is D2. So similarly, because it's literally just, now we're considering the bottom part only, so this would be equal to this and any other point chosen on. And now that you guys have already brought it up, then maybe I should say that this, the angle that's subtended by A and B on the upper part of the circle is 180 minus the bottom, and we'll discuss cyclic quadrilaterals later. But all you have to know is that all these angles. So if you choose one of them and choose one of these, then the sum is 180 degrees. So that's cyclic quadrilateral. It's pretty cool. Are we all together? Okay, cool. Another basic but important property is that if you take a chord and consider the center, so we subtend angle to the center, so this, and then take another chord. So I'm sure those who've done circle geometry knows that if you call this theta, then that's twice theta, right? And the nice thing about this one is that it can actually prove. So we don't have to, well, the other one was just a property that we assumed because it's a building block, and this comes from that, or doesn't really come from that building block, but this can actually be proven. So we'll construct a line here. So we consider a line here. And what can you tell me about this line, the red line, and this line? They're equal, right? Because the radius of the circle, since this was defined to be the center. So that's equal to that, right? And similarly, this is also equal to this, right? Because they're both the radiuses, the radii of the circle. So okay, any ideas now? Because remember, what do you want to prove that that's twice that? Yeah.
You just measure.
Measure. Unfortunately, that doesn't qualify as a proof. The reason is because if we made a slight difference here, put this here, and put that there, then it just works for that specific case. Only proving when you measure that it works for this, but that you don't actually prove that it works in general. So yeah, that's another thing with proofs in geometry. It's about general. It's not about if I measure this angle, then it works for everything. Unless they say this angle is that specific length. But I doubt you ever get a proof where you have to measure.
If you extend the line from can we name the triangle?
Oh, okay, sure. Yeah, that's actually a good idea. Naming.
If you extend the line from A to O past O, then
Past O.
yeah, past it, then A1. If we name each of those, A1.
So A1, this one.
A1.
And I'm guessing you call this A2.
Yeah, call that A2, and then C1 and C2, B1 and B2 as well. Then A1 plus O1 and O2 as well on the bottom.
I'll just erase this.
Then A1 plus C1 is O1.
Yes.
And A2 plus B2 is O2. I think I can't see which one is which.
Oh, okay, sorry. Okay, but I see what you mean, using the fact that they're vertically opposite.
Using angles in a triangle and then exterior angles in a triangle.
Oh, okay. Okay. So that plus that is equal to that,
Yeah.
right? Okay.
And then if you have both
And
of
then that
those,
is equal to that.
then it means that.
Okay, so can let me write it down. So what she's saying is A1 plus C1 is equal to O2, and that's a property of the exterior angle of the triangle. So if you have a triangle, extend this, so that plus that should equal to that. So x, y, that's x plus y, and it's really easy to see because sorry for that. I'm just going over this game. It's easy to see because if you use the sum of the angles here, this angle would be 180 minus x plus y because everything adds up to 180, and then this is a straight line, so these two add up to 180, so that's just x plus y. So yeah, she used that property there, and yeah.
Okay, and then A2 plus B2, I think, is it B2 or is it
B1.
Sure, I can't really see. Is O1. So O1 plus O2 is A1 plus A2 plus C1 plus B1.
Sorry, I'm just going to help you a little bit there. What type of triangles are you working with?
Isosceles, so those are
Yeah. I mean,
A and A1,
yeah.
B1, and
I mean,
A1
one.
is equal to C1,
yeah, and A2 is equal to
B1.
Yeah, I mean, once you see that, that's the trick, I guess. To see that that's
Yeah.
equal to that and that's equal to that, and then yeah, use what she's been doing now. So use that.
Because it's the radius of the circle.
I mean, yeah. I mean, I was gonna use a slightly different approach. Use the fact that find this. This is one. Okay, I was gonna call this x and this x and that y, and that's 180 minus 2x, and that's 180 minus 2y, and then this whole thing is just 2x plus 2y, so twice that. But it's essentially the same thing because you just have to spot that. Yeah, Mara.
Yeah, basically it's the same thing but the other way around.
Yeah. So yeah, I mean, how you finish it off doesn't really matter, but the main thing is to see that these are isosceles and subtract from there. Cool. So more circle theorems, they just don't end. So maybe for those of you that if you have a circle, chord, and center, then you have that. if you see a problem and it looks like the center, don't assume that it's the center and make it twice that. It's just, yeah, only if it's the same, only if you show that that's the center, then that property holds. Cool. And another property is that if you have a chord in a circle and its center, it's called a chord AB, and you have its center O, and if you drop a line that bisects these two, then that has to be 90 degrees. And also the other way around, if you drop a line onto the chord AB and it is 90 degrees, then these two have to be equal. And we're going to do a wonderful proof for it. So yeah, so we're going to first prove that if these two lines are equal, then this is 90 degrees, right? So, I mean, this one looks fairly standard, so I expect people to see it but quickly. Also, there's only one thing to see really, and then from there it follows. So I'll just go over it quickly. So we have that these two are equal because they radii of the circle. So AO is equal to OB, and okay, let's call this X. So AX is equal to XB because that's what the problem says. It gives you that and says you must prove that that's equal to that, and that's equal to 90, sorry. And OX is common amongst these two triangles. So remember, congruent triangles, all this triangle is exactly the same as this triangle, right? Because all the sides are the same. So OAX is congruent to OBX, right? There's a problem with that. Everyone can see why these two are equal, and yeah. Therefore, we know that angle OXA is equal to angle OXB, because the angles are also the same if they're congruent, not only the sides but the angles. Yeah, it follows. But we also know that this is a straight line, so OXB, OXA plus OXB is 180 degrees, right? Now, if you just give this a name, say you give it alpha, and then that's alpha plus, because it's the same, that's alpha is 180 degrees. So alpha is 90 degrees. So, yeah. Everyone understand that? So yeah, so if you have a line that cuts a chord and bisects it, bisect meaning cut it at its midpoint, then these, that's a right angle. And then the other way is to show that if we're given that a line from through the center cuts a chord at 90 degrees, we have to show that AX is actually equal to XB. And it's quite a similar proof to this one. So this one needs a bit more work, because remember, from congruent, if two triangles are congruent, you only have to know that if these two sides are equal and this, and the angle between them. So this angle is actually not between this and this, since it's equal. So it needs a bit more work to show that either the sides, yeah?
Don't you have a right angle and the hypotenuse side
Yeah.
and one other side?
I mean-
so they're congruent.
Like, does it need to be that at the side?
Yeah, I mean, you could take it as a property, but I mean, for someone who's never done, who's never seen this before or something, like they think that it's this property, but it's actually not. So, I mean, I'm gonna give a short proof. It's a really short proof, but yeah, you can take it as a property that if it's a right angle, and even though the sides are not the same, yeah, it follows. So.
Do you mind? Sorry, do you mind switching colors? We can't really see the red.
Okay, I'll just. Okay. So for this one, you know that these two lines are equal, right? This line is common amongst both triangles, and these two are equal. And then you want to show that A is equal to B. So I'll actually use Pythagoras for this. So you know that, let's call this B and this C, and that's C. Is that better for you guys? The black color. So you know that A squared plus B squared is equal to C squared. Just Pythagoras on this triangle, right? And did I call this B? Sorry. A squared plus D squared is C squared. And using Pythagoras on this triangle, we know that B squared plus D squared is equal to C squared, right? And if you take this to the other side, for the first equation, we get A squared is equal to C squared minus D squared, and B squared is equal to C squared minus D squared, right? And since these two things are equal, then the other side also has to be equal. So A squared is equal to B squared. And since they're both positive, we can't have negative, so both of them are the same. So A is equal to B. So yeah, that's one way of doing it. But of course, the other way is if you've done enough geometry to know that the right angle doesn't necessarily have to be between the two proportional sides for them to be congruent. Any questions?